Tensioning the Riemann hypothesis using vector polygons. By Gustavo Saravia Aramayo. La Paz, Bolivia, South America, 2026. This video is a presentation based on the original article prepared in 2025, which contains a higher level of detail and can be requested from the author. Exploring the Riemann hypothesis using vector polygons. Overview. In this work, we propose a novel approach to the Riemann hypothesis by linking the Dirichlet form of the Riemann zeta function with an auxiliary framework of vector summation. By using abstraction and tools from vector calculus, we derive a closed-form expression for the direct calculation of the imaginary parts of the non-trivial zeros of the zeta function, independently of the real part. Our results reveal a previously unidentified pattern of order in the distribution of these zeros, which could provide relevant evidence regarding the validity of the Riemann hypothesis. Theoretical framework. The Riemann hypothesis, formulated in 1859, is a conjecture concerning the distribution of the zeros of the Riemann zeta function, which is here expressed in the form of a Dirichlet series and which converges for all values of S whose real part is greater than 1. The Riemann hypothesis is important due to its connection with the distribution of prime numbers. Decades before Riemann, Leonhard Euler established an equivalence between the Riemann series and an infinite product formula over all prime numbers p, which converges for real values of S greater than 1. This convergence implies that the Euler product has no zeros in this region, since none of its factors vanish. The Riemann hypothesis concerns the zeros of the zeta function that lie outside the domain where the real part is greater than 1. This requires an analytic continuation of the zeta function that is well defined for all complex values of S. This analytic continuation possesses trivial zeros at the negative even integers, namely -2, -4, -6, and so forth. However, it also admits other zeros whose real part lies between 0 and 1, known as non-trivial zeros. Thus, the Riemann hypothesis states: the real part of every non-trivial zero of the Riemann zeta function is 1/2. Fundamental approach and idea. The Dirichlet form of the Riemann zeta function can be analyzed when we consider its connection with a geometric structure. Certain key parameters emerge when this geometric link is recognized. In this work, we present a central idea, to represent the summation in the Dirichlet form of the Riemann zeta function as a sum of two-dimensional vectors. When we plot this vector sum using the standard head-to-tail method, polygonal method, an irregular polygon is formed, with sides of different lengths. The requirement that the polygon must close provides a visual representation of the mathematical condition that the total sum must be equal to 0. Since the exponent S is complex number, each resulting term is also a complex number, which can be interpreted as a vector in the complex plane. The resulting sum, constructed using the head-to-tail, polygonal, method, forms a valid irregular polygon to which all concepts of plane geometry related to polygons can be applied. Our objective is to derive a symbolic expression to calculate the imaginary parts of the non-trivial zeros of the Riemann zeta function. To achieve this, we first express the general term of the Dirichlet series in its rectangular form using Euler's formula. In this way, we obtain the central expression shown here. N is a positive integer. S1 is the real part of the complex number S. S2 is the imaginary part of the complex number S. 1 over n to the power of S1 is the magnitude or modulus. S2 natural log of n is the direction angle of the vector associated with the modulus. The formula for the imaginary part, S2, is obtained by following a series of logical steps. An initial irregular polygon is formed, whose sides are the vectors implied by the rectangular form of the Dirichlet series of the Riemann zeta function. Then, each vector side has magnitude equal to 1 divided by n raised to the power of S1. The direction angle of each vector is the natural logarithm of n, measured from the horizontal axis. And here is the key: for the internal angles at the polygon's vertices, an initial estimate equal to the natural logarithm of n is used. This comes from the direction angle of the vector associated with that side. This value, the natural logarithm of n, acts as an initial condition. From vector geometry to the non-trivial zeros of the Riemann zeta function, a polygonal framework. Conceptual illustration showing the initial configuration of the polygon with initial parameters. In this context, the natural logarithm of n has been chosen due to its role as a scalar factor within the direction angle of the vector associated with the polygon's side. It provides a tentative value that is coherent with the proportion of the interior angles of the polygon, which are always well defined. Furthermore, the natural logarithm of n is not arbitrary but a strategic choice. It allows for flexibility in selecting a tentative interior angle. As will be shown shortly, this scalar value is then combined with a multiplying factor that acts as a correction, ensuring that the geometric properties of the polygon's interior angles are preserved. Now we multiply the initial direction angle of each vector by a positive scalar s2 greater than 0. This scaling increases the angular amplitude of the vector by a factor of s2, an opening effect, and decreases the internal vertex angle by an approximate factor of 1 over s2. Recall that s2 comes from the Dirichlet form of the zeta function expressed in rectangular coordinates. The required summation of the internal angles at the vertices of a closed irregular polygon is calculated using the ancient formula of plane geometry, pi times the number of sides minus 2, as shown here in the first equation. The fact that the polygon must be closed derives from the zero summation requirement in the Dirichlet series of the zeta function, for the calculation of its roots. The second equation shown here is the result of substituting the expressions of the angles of the constructed polygon, which can be found in the right-hand box. By simplifying, calculating, and isolating, or solving symbolically for S2, the final equation is obtained, which ultimately corresponds to our proposed formula for the direct calculation of the imaginary part of the non-trivial roots of the Riemann zeta function. Numerical exploration of the proposed formula. We will evaluate S2 for a range of n values, where n represents the number of terms in the Dirichlet series of the Riemann zeta function. When calculating S2, the enormous size of the factorials of n causes personal computers to overflow and crash. For this reason, it is necessary to use an equivalent expression using the log gamma function, based on an identity for the natural logarithm of a factorial. Then, we have generated an ordered table of S2 values calculated for a sequence of increasing integer values of n. This data set serves as a computational validation of the proposed formula. Note that the values of n are very large. When plotting n versus S2, a logarithmic scale is required on the x-axis. The shown graph presents an xy plot of n versus S2. The result is a straight line, revealing an essentially linear, orderly, and predictable behavior of S2 with respect to the original values of n. Direct calculation of the imaginary parts of the presumed non-trivial zeros of the Riemann zeta function, and comparison with known numerical values. We will now explore our proposal more deeply from a numerical perspective. Using a personal computer and a well-known software capable of performing arbitrary precision arithmetic, and applying our proposed formula in its log gamma form, we have computed values of S2 for very large integer values of n. Indisputably, the resulting values of S2 match the already known and officially accepted imaginary parts of the non-trivial zeros of the Riemann zeta function, as published by prominent researchers such as Andrew Audley's co. Now, we present some values of S2 calculated with our formula to a precision of 13 decimal digits. These values match the officially accepted non-trivial zeros of the Riemann zeta function, which were obtained using supercomputers and approximations with numerical methods. The values produced by our formula are in close agreement with these official reference values. N is the number of terms to be used in the Dirichlet form of the Riemann zeta function. S2 is the imaginary part of a Riemann zeta zero. First, using our formula, and then the officially accepted and publicly known value. Example 2, for the calculation of the second non-trivial zero of the Riemann zeta function. An integer with 30 digits has been used for the number of terms employed in the Dirichlet form of the zeta function. The imaginary part of the zero of the Riemann zeta function, obtained using our proposed formula, matches the imaginary part of the officially accepted Riemann zeta zero, with a precision of 13 digits. Example 3, calculation of the 17th non-trivial zero of the Riemann zeta function. An integer with 96 digits has been used for the number of terms employed in the Dirichlet form of the zeta function. The imaginary part of the zero of the Riemann zeta function, obtained using our proposed formula, matches the imaginary part of the officially accepted Riemann zeta zero, with a precision of 38 digits. Conclusions. The results of this work demonstrate a strong correspondence between the imaginary parts of the non-trivial zeros of the Riemann zeta function and our proposed formula. The values of S2, calculated for large integer values of n, accurately reproduce the imaginary parts of the known non-trivial zeros, as published by authoritative sources such as Andrew Audley's Co. This evidence supports the hypothesis that the imaginary components of the non-trivial zeros may arise from a deeper arithmetic geometric mechanism, as suggested by our model of the irregular closed polygon, whose idealized internal angles of the vertices adhere to geometric laws with complete coherence. The observed linearity in the behavior of S2 as a function of n, when plotted on a logarithmic scale, suggests that the imaginary parts exhibit an ordered and predictable structure, challenging the notion that their nature is irregular or random. Our proposal suggests that these imaginary components, S2, can be obtained directly from the Dirichlet form of the Riemann zeta function, without needing the real part, S1, of the zeros. This means they can be derived independently, in a clear and ordered way, from arithmetic and geometric principles contained in our formulation. In addition, our formula suggests that there are infinitely many values of S2, and many of them do not appear in the official tables of known zeros. This leads to an important question: does each value of S2 found here correspond to a zero whose real part, S1, is equal to 1/2? Another key point is that the imaginary parts of the non-trivial zeros can be calculated accurately using a very large, but still finite, number of terms from the Dirichlet series. This raises a deeper question: are these zeros truly absolute? And if they are, why do they not require an infinite number of terms for their calculation? From this perspective, it follows that, at least in a partial sense, the Riemann hypothesis can be questioned or put under tension. Our results offer an alternative, formula-based way to obtain the imaginary parts of the zeros. Moreover, the fact that our model is built on a logical, mathematical, and geometric abstraction gives additional support to its credibility and potential implications. Thank you.